Look at the nearest cell tower. It is rooted in steel and concrete, serving a strictly local radius. The moment you drive past its invisible perimeter into the wilderness, your $1,000 smartphone loses its connection and shuts you off from the world. To solve these dead zones, the telecommunications industry is moving toward direct-to-device, or D2D. This technology allows a standard, unmodified smartphone to bypass terrestrial towers and connect straight to a satellite in orbit. The hardware for this is already in the hands of millions. Apple successfully launched Emergency SOS via satellite using standard iPhones, proving that consumer devices can communicate with space without specialized antennas. While firing off a low-bandwidth emergency text is a proven reality, scaling that connection to handle millions of simultaneous high-data users creates a massive physical barrier. In a non-terrestrial network, your cell tower is a satellite blazing through low Earth orbit at 17,000 miles per hour. Immediately, you hit a latency hurdle. Your phone signal must travel hundreds of miles through the atmosphere, hit the satellite, and travel the same distance back. Then there is the Doppler effect. Because the satellite moves with extreme velocity, it warps the radio waves, compressing them as it approaches your phone and stretching them as it flies away. These shifting coverage areas create constant dynamic interference, making orbital connections inherently fragile. Applying the static rules of a terrestrial network to an orbital environment breaks the system. The physics of space makes stable, high-speed connections impossible for a traditional network to manage. Engineers on the ground can manually optimize traffic because terrestrial cell towers stay put. In space, every data packet is fighting against high-velocity motion and changing network conditions. Industry leaders at events like Satellite 2026 argue that manual systems cannot scale in this environment. They are calling for an architectural philosophy known as AI by design. In this model, artificial intelligence is not a software add-on or an afterthought. It is woven into the foundational architecture of the radio access network. To successfully bridge the gap to D2D, the network must evolve from a passive relayer of signals into a cognitive brain that can adapt autonomously to orbital mechanics. This embedded AI acts in real time to analyze the satellite's trajectory and proactively compensate for severe Doppler shifts. The AI reverse warps the signal frequency as it leaves the antenna, tricking the smartphone into perceiving the satellite as perfectly stationary. Simultaneously, it calculates timing advances so data frames do not collide. Finally, it dynamically steers phased array antennas to maintain a solid lock. AI serves as the mathematical bridge that allows terrestrial hardware to function in an orbital reality, unlocking the door to mass commercial scale. With the physics of scaling now technically viable, the telecommunications industry is pivoting from experimental trials to massive commercial deployments. Amazon underscored this shift with its $11.6 billion acquisition of Globalstar, integrating their low Earth orbit assets into the Amazon Leo project. Amazon and other cloud hyperscalers are targeting legacy satellite operators to secure pre-licensed radio spectrum. This spectrum is the digital real estate required to build a direct-to-device network that works anywhere, bypassing localized regulatory hurdles. The corporate race is centered on establishing a monopoly over the physical spectrum layer that makes global connectivity possible. These orbital networks will integrate with terrestrial infrastructure. Users will move from remote landscapes to dense cities without noticing the switch from Earth to space. This enables a shift from emergency fallback services to everyday broadband for millions of simultaneous users. This infrastructure replaces the static physical tower with a smart, borderless grid operating from the atmosphere. By combining direct-to-device technology with AI-driven architectures, these self-optimizing cognitive networks are capable of redefining global telecommunications.